Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Okay, this is the homework for lecture 98. Okay, number one, a positive charge, Q1, is located at the origin. Another positive charge, Q2, is located at x equals A. What is the electric field in the region X greater than A? No numbers, just symbols. All right, let's see here. So we'll draw a diagram. We have Q1 located at x equals 0 and Q2 located at x equals A. So the distance between these two is A. And we want to consider the region x greater than A. So just pick some point over here. This will be where our test charge is located. It's a distance x away. So this distance is x. The distance to charge 2, however, from the test charge is the distance x minus A. So this is x minus A away. This is x away. So what's the electric field? The electric field is E1, the electric field due to charge 1, plus the electric field due to charge 2. Notice that they're both pushing A to the right, so in the positive direction. So the sign on both of these will be positive, and this is just equal to K times Q1 divided by x squared, that's this one here, plus K Q2 divided by x minus A squared. And that is problem number one. All right, problem number two. Using the same configuration from problem one, describe the electric field when x is much, much greater than A, very far away. Well, I left the work from the last problem up here. So what happens when x is very far, far away? So this was 1. This will be number 2. So if x is much, much greater than A, what does that mean? Well, that means that x minus A is approximately equal to x. So if that's the case, then we would rewrite E as K Q1 over x squared plus K Q2 over x minus A squared, but that becomes just x squared, right? So we can approximate that as x squared. I'll write the approximation symbols here. So now this is, I can factor out the k and the 1 over x squared. So I get k over x squared times q1 plus q2. And that we can just write as k big Q over x squared, where big Q, of course, is the sum of the charges. And so this, if you think about it, if I wanted to have, say, a charge of minus 2, and I said that each electron has a charge of minus 1, if I plunk one down at x equals 0, I can't plunk another one down at x equals 0. It'll have to be a short distance away, call it A. Well, as long as the distances I'm talking about, where my field, where I want to consider my field at, is bigger than A, then I can treat them as occupying the same space. And so I can say that at x equals 0, there's a charge of minus 2. So that's basically what this is all about. Now, when we get into Gauss's law, we will learn that there's actually clever ways that we can create distributions of charges so that they behave as if they're at a single point. But we'll get to that later. So that's problem two. Okay, problem number three. With the same configuration as before, what is the electric field in the region x greater than 0 but less than A? Okay, so let's look at that. So I'll draw a new diagram for this one. This is number 3. So in this case, we'll have Q1 at x equals 0. Q2 will still be at x equals A. This is still A away. But I want to put my test charge right here at x. So first thing to notice is that the field from charge 1 will the force that results, remember with test charges, we always consider them to be positive test charges. So the direction of the field is the direction of the force if the test charge was positive. So if this is positive and this is positive, there will be a repulsion, and it will be in this direction, so to the right. However, charge 2 is to the right of x, our test charge, and so it will be acting to the left. So these are going to be oppositely directed. That'll be reflected in the signs. The distance is, well, this distance here is just x, and this distance here is actually a minus x. So how do we write this? E. First we'll write for charge 1, so k q1 over x squared, and that'll be in the positive direction or to the right, plus the charge, the field because of charge 2, which will be acting to the left, so we'll make that minus k q2 over a minus x squared. Now, note you can, I'll put note, a minus x squared is the same thing as x minus a squared. So that can be handy. Sometimes you like to write it as x minus a, and you can certainly do that here. So that's problem 3. Okay, problem number 4. If q1 equals q2, and remember these are both positive, where does x equal 0? Okay. So that, I should have been a little more explanatory on that. That was for the situation, I guess maybe not. You can kind of see that in the region where x is greater than a, there is no region where it's equal to 0, except out at maybe infinity in the limit. But you can see from what we talked about before, in problem 3, we had it parked in between the two charges. And so charge 1 is acting to push it to the right, and charge 2 is acting to push it to the left. So you can see that there might be a situation where these two balance out perfectly, and we have an electric field of 0. So that's what we're looking for here. So we'll let Q1 and Q2 be equal. So this will be problem number 4. And we'll just let Q1 equal Q2 equal Q. So we can then write the electric field as K times Q times 1 over x squared minus 1 over x minus a squared. And so now let's ask, well, could this possibly be 0, right? Let's let it be equal to 0 and see what we get. We can see that the K, the Coulomb's constant, and the charge just cancel out, and so we're left with the condition that 1 over x squared is equal to 1 over x minus a squared, which means that x minus a squared is equal to x squared. Okay, so let's expand this square. That would give me x squared minus 2ax plus a squared equals x squared. Well, x squared equals x squared, those just cancel. And so we're left with a squared equals 2ax. Solve for x. That gives us that x is equal to 1/2 a. And that's not surprising that you would find that the force exactly cancels right in the middle if Q1 is equal to Q2. Okay, finally, problem number 5. Let Q2 equal minus Q and Q1 equal plus Q. This is called a dipole. In the region x much greater than a, show that the electric field is approximately minus 2k qa over x cubed. Note that qa is called the dipole moment vector. The field falls off to 0 very far away from the dipole. You can think of this as the charges canceling at distances very far away. So this is a tricky problem because we need to consider far away distances, but not too far away, such that the charge just cancels out. So let's set it up. We'll write a plus charge at x equals 0, and then a distance a away, we will have the minus charge like this, but we will consider some point over here at x. So what does the electric field look like? Well, the electric field from the positive charge will, of course, be repulsive, and that will be kq over x squared. But the negative charge will have an attractive force on the test charge because we assume test charges are positive. And so this will have a minus sign in front of it, and it will be a distance a, or x minus a, away. And so we can write this as kq, because the magnitude is the same, over x minus a quantity squared. So let's see, what do we do with that then? Well, we can factor out the kq. So we kq times 1 over x squared minus 1 over x minus a squared. Now it's just a little bit of fraction math, right? So we can multiply the two denominators together to get a common denominator, and that'll give me x minus a squared minus x squared, all divided by x squared times x minus a squared. And that, if I just multiply this out, we get kq times x squared minus 2ax plus a squared minus x squared divided by x squared times x minus a squared. So the x squareds will cancel. That leaves me with kq a squared minus 2ax divided by x squared times x minus a squared. So let's impose the condition that x is greater than a, or much greater than a, but not too much, right? Such that x minus a is approximately x. Then what happens? Well, now the electric field is equal to kq times a squared minus 2ax over, well, if x minus a is approximately x, then x squared times x squared gives me x to the fourth, which is equal to, and I'm going to divide that into each term. It's going to give me kq, and I'll get the a squared over x to the fourth minus 2ax over x to the fourth is just over x cubed. And so if we're pretty far away, we can see that the x to the fourth term is going to die off faster than the x cubed term here. That is within the denominator. So this one is going to go away, and so that the electric field is approximately going to be given by kq, and then we have a negative sign there, and there's a 2a over x cubed. Let me just rewrite that. That's going to be minus 2kqa over x cubed, where q times a is what we usually call our dipole moment. So usually the dipole moment is p. So if I let p, and it's usually a vector, equal q times a, which of course is a vector, but this is 1D, so I guess the vector nature of it is lost. Then we can write that the electric field due to this dipole is equal to minus 2k p all over r cubed, or x cubed, sorry, messed that up, x cubed. And so that's the classic dipole behavior, is that the field decreases like the inverse of the cube rather than just the square. And this physically, it makes sense because the dipole, the charges are kind of canceling each other, right? And so you expect it to drop off much faster than it would if you did not have this kind of charge cancellation effect in there. But I suspect we'll talk a lot more about dipoles in the future. So that's it.